Dear students, welcome to our science episodes. Today we are going to discuss radioactivity and nuclear energy. Radioactivity and nuclear energy. First, let's remember what is an atom. Yes, the atom is the building block of all matter. The atom consists of a nucleus at the center, surrounded by electrons, revolving around it in certain energy levels. The mass of the atom is concentrated in the nucleus, which contains two different particles, protons and neutrons. The composition of the atom is responsible for the physical and chemical properties of the element. The chemical reactions between atoms occur through their outermost electrons, while the nuclear reaction, if it is a nuclear reaction, not just a chemical reaction, it will occur due to the change in the number of protons and neutrons inside the nucleus. Therefore, the nuclear energy is stored in the nucleus of the atom. Why positively charged protons are found inside the nucleus without repulsion? If you can see here, these red particles are the positively charged protons. And the question is, why there is no repulsion between them? How they are attached to each other like this inside the nucleus? This is due to the presence of a force inside the nucleus which leads to binding. This force will bind the nucleus components together and it will overcome the repulsion force between the positively charged protons. This force is called the nuclear binding force. This force is the source that gives the atom its tremendous power, known as nuclear energy. Again, let's wrap it up. There are positive particles, positively charged particles inside the nucleus. Suppose this is the nucleus. The red particles are the protons and the white particles are the neutrons. And the question is, why there is no repulsion? We all know that two positive charged particles repel each other. Why there is no repulsion here? Because there is another stronger force called nuclear binding force, which binds the protons and the neutrons together. This force is the source of the nuclear energy inside the nucleus of the atom. If we want to define the nuclear binding force, it is the force needed for binding the nucleus components and overcoming the repulsion forces between the positively charged protons. Radioactivity phenomena. Look at this picture. As we said, the nucleus of the atom has two types of particles, protons and neutrons. If the nucleus of the atom have number of protons more than the number required for its stability, this will increase the nuclear energy inside the nucleus, and therefore the atom has to get rid of these excess energy in the form of invisible radiations, alpha radiations, beta radiations, and gamma radiations. Can we see these radiations? No, I told you that they are invisible. You can't see them. This is called the radioactivity phenomena. And the radioactivity, or these radiations, were discovered by a French scientist called Henri Becquerel in 1896. He discovered the emission of unseen rays from the uranium element. These rays have the ability to penetrate solid objects. Radioactive elements. They are the elements whose atoms, nuclei and nuclei is the plural word for nucleus. So nucleus plus nucleus and nucleus are called nuclei. Two and more nucleus are called nuclei. They contain a number of neutrons more than the number required for their stability. So as a result, the atom will get rid of excess radiation in the form of radioactive phenomena. Examples for radioactive elements: radium, polonium, selenium, rubidium, and uranium, cesium, and zircon. Again, radioactivity phenomena, if we want to define it, it is the spontaneous decay of the atom's nuclei of some radioactive elements present in nature in an attempt to achieve a more stable composition. So why the atoms of the radioactive elements are showing radioactivity phenomena? Because they want to reach stability. They are emitting energy in the form of invisible radiations in order to reach stability. Of course, due to presence of more neutrons in the nuclei of the atoms. The previous radioactivity phenomenon was natural, while this radioactivity is artificial. How radioactivity could be artificial? This is another type of radioactivity, which is known as artificial radioactivity. The radiation or the nuclear energy that is released during what? During nuclear reactions. And these nuclear reactions are in nuclear reactors, not regular labs, and they can be controlled and used in safe uses. While nuclear bombs or nuclear weapons, they can't be controlled and they are used in military uses. So the artificial radioactivity, it is also the radiation or the nuclear energy that is released during nuclear reactions or nuclear bombs. Nuclear reactions are safe, and nuclear bombs and nuclear weapons are very harmful and dangerous. There are also peaceful uses of nuclear energy or radioactive elements, like in the medical field for diagnosing some diseases or treating others, like cancer, for example. In the agricultural field, to remove the pests and improve some plants. In the industrial field, to convert sand to silicon. And silicon sheets are used in computer processors and electric appliances. In the electricity generation field, where we can use the nuclear energy to boil water. And when the water will boil, the produced water steam is used to operate turbines to generate electricity. Space exploration field, and it's used as a nuclear fuel in rockets that fly in space. The last one is in drilling field for petroleum and underground water. So these are the peaceful uses of nuclear energy or the radioactive elements. What about the harmful effects? The harmful effect is the radioactive pollution, radiation pollution. It is the increase of amount of radiation in the environment. And the sources are, for example, natural sources like the radioactive materials found on Earth's surfaces, or the cosmic radiation coming from the outer space. While the artificial sources, the explosion of nuclear bombs, the nuclear reactors, as you can see here, this was a real example of an explosion of the Russian reactor of Chernobyl. It happened on the 26th of April, 1986. It was a result of an error in operational error inside the reactor. It resulted in melting of the reactor core and a very huge nuclear explosion and release of many radioactive elements. These elements, as you can see here, they formed an atomic cloud. They contaminated air. The polluted cloud was carried by the wind to many countries in Europe. And the rain fell in May, in the month of May. I mean in summer, carrying radioactive elements to Earth's surface. The plants and the soil were polluted as well by the radioactive isotopes. Cows and sheep ate these plants. Their meat and milk products were also polluted. And then the radiation harmful effects were transferred to humans all over the world. Not only humans, animals, plants. Here you can see this is a nuclear reactor, and the polluted radioactive waste will result in air contamination, and then when the rain will fall down, it will result in water contamination of the rivers, of the soil, and then soil contamination at last. And then who depends on the soil? Of course, plants, animals, and also human beings. They are all affected. The radiation effects on the human body. After exposure to large dose of radiation for a very short time, there will be bone marrow, spleen, digestive system, and central nervous system damage. This means that the bones will be affected, the spleen will be affected, the whole digestive system, not only the spleen, and also the nervous system will be affected. If the exposure is to a small dose of radiation and for a long time, there will be physical effects, like effects that appear on the body, like for example skin cancer, genetic effects, as some changes in the sex chromosomes resulting in abnormal birth, cellular effects, which means changes inside the cell itself, in the cell composition. And here are some pictures from the disaster of explosion in Chernobyl. This means that radiation effects on the human body is very harmful. How can we measure radiation? We can measure radiation in sievert. 1 millisievert equal 10 to the power -3 sievert. It is the international measuring unit of nuclear radiation absorbed by the human body. And the maximum safe radiation shouldn't exceed 20 millisievert for the workers who work in radiation field per year. For public, it's only 1 millisievert per year. So for the workers, 20 per year. And for public, it's only 1. The safe dose of nuclear radiation depends on the age of the person, whether you are young or old, the period of time in which the person is exposed to nuclear radiation, which means the time of exposure, whether it is short or long. And finally, the part of human body that is exposed to the nuclear radiation. Dear students, thank you for watching and waiting for you in other episodes.